All right. So previously, last time, we were able to talk about, in addition to the formation of the solar system, we also talked about how the features that we see on Earth are used to educate us and give us information about other planets. And we'll see that as a common theme. That basically, if we can do something on Earth and we see a similar effect in the universe, we just assume they're the same thing. And again, that word assumption can make it sound like this is a weak process, but it's actually quite strong and based on data. So what I mean by that, and specifically it might sound more convincing, if we can in the lab see the spectrum for hydrogen, right, and then we look at a star and we see the same spectrum, we conclude that it's hydrogen. I think conclude is a better word than assume, probably. But that there is this desire sometimes. People say, well, what if it's different? Well, remember, we have that idea of Occam's razor, which is we just accept the simplest explanation until something simpler comes along. We don't make things overly complicated. So in that sense, the Earth is our test bed of ideas. We look at features on the Earth and we can look at them directly and interact with them. And then when and some of those features include things like plate tectonics. Um, we saw, mountains cratering, riverbeds. Oh, I didn't put the. I'm still getting back into the hang of this too. Riverbeds, which you can see here, cratering, volcanoes. These are all features we can see. Hold on, there's something wrong with the ratio here. Stuff on my screen. There we go. Is this something is I wanted to show here? Yeah. So we have different features of our different terrestrial planets. All right, and this is what we're really going to talk about and expand on. Now, let's see. We talked about being geologically active, and as that's a planet being alive. And we talked about this lithosphere layer, right? This outer layer of the crust and mantle. And we saw that for objects of various size, Earth and Venus, the lithosphere is still fairly thin, but for geologically dead objects, the lithosphere was quite big. All right? Basically, when the dotted line gets to the core, the planet's done. It can't live anymore. All right? That means no more earthquakes, no more geologic activity, nothing like that. So again, keep in mind, we're just reviewing. So we talked about different density layers and things like that. And another thing we talked about was the ability for rocks to stretch and be quite malleable, all right, under certain conditions. So rocks aren't as rigid as you think they are. We talked about the convection cycle, the heat cycle inside the planet, and talked about sources of heat over time. And we sort of saw how the Earth worked, how features on the Earth work. We also talked about the Earth's magnetic field, right? And how the magnetic field creates these aurora borealises, and the field deflects solar wind. All right. So if we had a weak magnetic field, for instance, we couldn't survive on Earth because too many harmful particles would get in to the Earth. So that's something to note. And we ended on we talked about seismic waves that give us the information about the interior of the planet, right? And so now we want to look at how the processes that shape our surface. That's what we ended with. We're going to look at the other planets, learn about them, and see, or the terrestrial planets, and see how those surfaces, those features, so we have here, come to play a role in these other planets. All right, we talked about erosion, and we talked about the atmosphere. We'll talk about the atmosphere again and radiation protection. Where we ended was with we're gonna talk about other things. We talked about the greenhouse effect. We're going to talk about now other planets. All right. So we're going to start with our geologically dead objects, Mercury and the Moon. Now you might ask, why are we lumping Mercury and the Moon together? Well, if you look at Mercury and the Moon on our PowerPoint presentation, you will notice that they look pretty similar. Mercury's got a little bit of discoloration, but if you look at them in the right lights, they're almost indistinguishable. You wouldn't know that one, without the label, it would be hard to tell them apart. But the question is, now that these things are dead, can we conclude that they were alive? And that's what they want to look at. So can we find features that tell us about these things? So if we look here, we can see some evidence of volcanism, right? In the Mara here, these dark spots that were probably left by lava. So so there's probably some volcanic activity, but there's none at present. But again, we look at those features. Mercury, so you'll notice now this really does look like the moon, right? This is a close-up view of Mercury's surface. If you're wondering how close, the scale of the image is given here. So that length is 50 kilometers. And Mercury has a mixture of heavily cratered and smooth parts of its surface. And the smooth regions are like the ancient lava flows. All right. And that's what lava does. It sort of smooths the surface. So if you have a lot of smoothness, that's indicative of ancient volcanoes. But of course, you have impact cratering, which probably still continues, making it look like it does. You'll notice the impact craters are still very well formed, which means, for instance, there's no wind or anything like that today on Mercury. We can see evidence of impacts from the other side of Mercury on Mercury. That's what this Chloris Basin is. And we can see these are the sort of the two sides of the impact. We can see cracks on the other end of Mercury from this giant impact. And what that tells us is that Mercury is almost all core, right? Because if there was a lithosphere active surface, that would have absorbed a lot of that impact. The tectonics in Mercury, we see, we see these cliffs, these cliff-like features, and recent geology on Mercury. Okay, so if we're looking at this picture, what are we looking at here? So these are thought to be hollows that are formed as easily vaporized minerals escape. And this is kind of interesting because it's thought that comets and asteroids might be the same, that there are these gas chambers that we could expel gas from, but the comets and asteroids would be so much smaller that you could use that to change their course. Now, unfortunately, I do know one of the people who was involved with that work, and I should say no more about it. So as far as geologic activity goes, we have we have Mercury and the Moon are dead. Now, when we go on to say Mars, right? Mars geologically is a dying planet. So Mars is still geologically active, but barely. All right. So let's look at some Mars quick facts. Mars versus the Earth. All right. So Mars is about has about 50% the radius of the Earth, but only 10% of the Earth's mass. It's 1.5 astronomical units from the Sun, if you remember, because it's been a while. An astronomical unit is the distance from the Earth to the Sun. It's the basis of all our astronomical measurements. It has about the same axis tilt as the Earth, and it has a similar rotation period. So what does that mean? That means a day on Mars is almost the length as a day on Earth. It has a thin carbon dioxide atmosphere, which is little greenhouse. Now, you might be saying, well, wait a minute, carbon dioxide is a greenhouse gas. And you're right. Carbon dioxide is, but the word thin is the important word here. There's not much of it there. So the main difference between Mars and Earth is that Mars is smaller. And remember, last time we talked about the size, of an object. Larger objects take longer to cool down than smaller objects, right? We talked about this with a cup of coffee. If you have a little cup of coffee and a giant, bucket of coffee or pot of coffee, the cup cools much faster. Okay. So the seasons on Mars as it rotates, and it takes quite, the Martian year is a bit longer than the Earth year as it goes around. You can look that up in a table though. I'll give you that exact number. I can't remember it off the top of my head. But the seasons on Mars are more extreme because unlike Earth, the distance, the orbit of Mars is actually more elliptical. So what that means is that the sun is less in the center, more in the focus here, and Mars will have its northern hemisphere, I believe, where it'll tell us here. So the northern hemisphere summer is long and cool, and the summer hemisphere winter is long and frigid. And when we get to the other side, the northern hemisphere winter is brief and mild, and the southern hemisphere summer is brief and warm. So the seasons are a little more extreme in the southern hemisphere. All right, and that's mainly because winter is the worst. So it's so because of its elliptical orbit, whereas with the Earth only the axis tilts, right? You can see the way it's tilted. The axis tilt plays the largest role in the changes in seasons on Earth because our orbit is only very slightly elliptical, whereas Mars's orbit is much more elliptical. So that distance is going to play a role. But we can see some interesting things on Mars. You know, Mars is the planet we've been to the most. So we've studied and mapped it a lot. Several missions have gone there, like the Curiosity missions and the rovers. And it's important to understand that sending objects to Mars and getting like on the ground pictures of it is pretty new stuff. My father, for instance, was a junior editor at a newspaper in San Francisco. They called it the Chronicle. And he was there when the Voyager missions sent the first photographs back to NASA, and NASA distributed the first photos of Mars to the newspaper. And so that was only about 10 years before I was born. And if we were in class, you'd be making comments about how I'm not as old. I don't seem all that old. So, so our understanding, this type of level of understanding Mars is very new. And the ability to look at these pictures is really fascinating. But you'll notice all our pictures of Mars, like from 2001, we can see a dust storm on Mars. It covers the whole planet. And we can see just before the dust storm and then during the dust storm. And other things we can see from our missions to Mars and our ability to take pictures is we wanted to look for and see if we could find evidence of liquid water on Mars, right? That's the big golden, the big find for Mars. And we want to find liquid water because everywhere we found liquid water on Earth, we found life. So finding liquid water is a big deal. There's plenty of water in the solar system. Most of it's frozen. But we can see that that we have what look like riverbeds here on Mars, and so we see the same thing from dried up riverbeds on Earth. So, you know, you look at one, you look at the other. Now this is kind of cool. This is a big global picture of Mars. You can see Mount Olympus is actually taller than Mount Everest, and you can see some of these geologic features as we go around to Mars and looking at different parts. So you can see some of the different missions, like the Phoenix landing site, the Viking 2 landing site, the Curiosity landing site. So these X's are where things have landed. The Pathfinder was a big one. The Opportunity and the ExoMars landing site, that was a big mission. You'll notice much of Mars's northern hemisphere is covered by volcanoes and lava plains with some erosional features, and then the southern hemisphere is covered by ancient craters and some erosional features. So we can sort of get a picture of what Mars looks like. Okay? And we can see here that volcanoes were active as recent as about 180 million years ago. That seems like a long time, but in a solar system where we're really talking about billions of years, 180 in geologic time, 180 million years is, you know, it's not that long. But, you know, it's not that short either. So we can see some evidence of past tectonic activity, you know, these large looking fault lines. all right, that go that are here. But again, once a planet geologically passes away, there's no more earthquakes or tectonic shifts. So there's just more pictures. All right, so let's see what we all really wanted to see, right? Which is the surface of Mars. So what you're looking at here is northern Arizona and Earth, but here you're actually on the sentence of Mars in the Endurance crater. And you'll notice, if you look here, these are two places that used to, in the far past, have liquid water. And this was from the Opportunity rover, which also the Opportunity rover, it found this evidence. We might want to focus on what this evidence is, which is in this little paragraph here. The mineral hematite is typically formed in salty water environment. We can see that it can be formed here in Arizona, where water has not been in a very long time. And I want you to notice the scale here of Mars. We are on the surface, and we can see the same thing. All right, and so that's what it looks like when they're kind of similar looking areas where water has not been in many millions of years, but we can still see evidence of water. Okay. All right. Now you'll notice here, this is Earth. It might not be unexciting, but here we have a picture of Mars. And I like these. I don't know. I've never ceased to be fascinated, and I haven't taught this. This section would be something a student would talk about in a presentation, so I haven't taught Mars in a long time. And it's pretty incredible just that you're looking at a different planet here. This is Mars. But again, it's looking at it, there's more to it than just looking at it, right? We can see the same pebble structure deposited in rocks that are very similar to stream bed, rock formations that form in stream beds. So again, when you see two of the same thing, there's no reason to think they formed in different ways. Okay? So any questions about Mars so far? Nope. It's pretty cool. We can look here at these layered rock characteristics. The layers of rocks are characteristic of sedimentation by water. So we sort of see the effects of water having flowing through everything, but it seems that the actual water itself was a long time ago at Mars. All right. That's a good question. Is there any bacteria on Mars? I don't think we've found any bacteria on Mars because bacteria is life. So bacteria is I believe, classified as alive, and that would be a huge thing or a huge discovery. We keep looking for microbial life on Mars, but I don't think we found it yet. Again, today most of the water lies frozen underground. And there's recent evidence suggests, but that's a suggestion, not conclusive, that small-scale flow of salty water at or near the surface here, seen as seasonally changing dark streaks. So there might be some flow, but if there's no surface water, there's unlikely to be bacteria. So we'd want to find pockets of water, and then we're hoping if we can find pockets of liquid water, we can find traces of bacteria. If you want to scare yourself, though, there's a fun episode of Doctor Who called "The Waters of Mars." That was one of the scarier episodes. It was pretty good. It aired years ago, though. If you're looking for a horror story version of Mars. So why did Mars change? Well, there's a few differences between Mars, not only size being one of them, but you'll notice Mars today, it hasn't looked like Earth for about 3 billion years, and the greenhouse effect with a thicker atmosphere probably kept the surface warmer before that time, but somehow Mars lost most of its atmosphere. And again, you'll notice here, early Mars probably had a vibrant magnetic field, much like Earth, which would protect it and keep the atmosphere. If the solar wind is reflected, one of the things that does is it keeps the atmosphere stably on the planet. If the magnetic field slows down and gets weaker over time, the atmosphere evaporates or gets blown off into space. Now, that will happen to the Earth eventually as well. The Earth will cool, the core will cool, and the temperature, the Earth will not be able to maintain its magnetic field. And when that happens, that's pretty much, well, I mean, that and the end of geologic activity will pretty much make the planet unhospitable. So, all right. So we can see here that this theorized magnetic field would have preserved the atmosphere. Well, we just said that. I'm not going to go over it. And today we can see hydrogen, oxygen, and carbon in Mars, and we can sort of get an idea. We can see the atmosphere being blown out literally into space as we look at it. So, these are the gases coming from Mars, and we can see today how the lack of magnetic field is stripping that stuff away. So now that we've seen Mars, we're ready to go on to our next terrestrial world, which is Venus. Okay. And but before that, we already talked about that. That's good. Now Venus is a bit different looking. And Venus was hard to penetrate because of its very thick atmosphere. Now Mars we could sort of think of as not having enough atmosphere, and so there's not enough greenhouse gas, and the atmosphere is thin, and the planet is cold. Venus, on the other hand, has way too much greenhouse effect, and it's very cloudy, and it's only very recently that we've been able to look at that we've sent missions to Venus to actually look at when not looking at visible light, because that can't get through the cloud layers, but using infrared to get ideas of the surface of Venus. All right. So if we look here, let's look at some of these features. So we can see this is kind of cool. These are twin volcanoes, so these are very similar to like what we'd see on the Hawaiian Islands. We can see that there is impact cratering on Venus, and it seems to be relatively evenly distributed. So the central image here shows the full surface of Venus, 98% of which was mapped by Magellan. And we want to notice the three large elevated quote-unquote continents. They're called Istar Terra, Lada Terra, and Aphrodite Terra. Okay, these areas here. And we look at them, we can see tectonic forces have sort of fractured and twisted the crust. And we can see some of these interesting features behind these volcanoes. And it's surrounded by, these are evidence of tectonic stress marks. So there's lots of active volcanoes on Venus. All right, lots of them. And we can see that Venus is a hot house. Well, we'll see it as a hot house, but we'll notice that the impact craters, right? It has them, but they are less of them than Mercury and Mars. And we're going to see that's not because Venus gets hit any less, but Venus is geologically active, so the volcanoes and the lava can fill in those craters and change the surface features. Also, I love the picture, the twin volcanoes, and there's a lot of volcanoes on Venus. Again, we're looking at different worlds here, exploring different things. We can see the thermal temperature of the lava, and we can see the volcanoes themselves, which is pretty exciting. I want to look here because this is rather interesting. And again, this fractured and contoured surface indicates tectonic stresses. Now, what we're going to see with Venus is that it's so volcanically active that the surface seems to get paved pretty frequently, and we'll see pictures of that. And what that means is that fault lines, you'd expect the fault lines even to get smoothed over eventually, but they're probably creating new fractures and things like that as Venus becomes active. So this is from this is a photo of Venus's surface. As you can see, it's cracked, but it's very smooth. I mean, relatively speaking. And this is photos of rocks taken by a Russian lander, and it shows very little erosion. All right, so there's not a lot of wind. Now, Venus, the lander here can only last about 10 to 30 minutes before it just shuts down due to heat. The heat in Venus, I think we covered briefly, is extreme, and it's about 450 degrees centigrade or about 830 degrees Fahrenheit. So to put that in perspective, your oven in your kitchen probably goes up to about 500 degrees Fahrenheit. And I want to ask you if you would put your fancy iPhone in the oven at 500 degrees. What do you think? Nope, probably wouldn't do that, right? So if we're not putting, so you can imagine how hard it is to design electronics that can survive for any length of time at nearly 800, 900 degrees Fahrenheit. It's very difficult. But we can see here these pictures. We know very little detail like this of Venus's surface. So does Venus have plate tectonics is an interesting question. So most of Earth's major geological features can be attributed to plate tectonics, which gradually remake our surface. But Venus doesn't appear to really have continental plates, but its entire surface seems to have been repaved 750 million years ago. So it's hard to know because it could just be that the evidence of that plate tectonics just gets covered very quickly, making it hard to discern. So we have to be careful there when we look at it. And actually, fun fact, we talk about colonizing Mars a lot. And with Mars, there are a ton of problems with colonizing, with really colonizing Mars. And Venus actually would be pretty easy to colonize. The only thing you would need to do is keep your structure at a certain elevation where it would be temperate. And because of the clouds, you could do things like reclimate water. And then once you had a structure where you could reclimate the water, you could be just fine. That being said, it's what you would call it. Getting a structure to float is kind of hard. So that's that's the challenge. There's one big challenge with Venus. There's several major challenges with Mars. And I say that because Venus's gravity is similar to Earth's. So because of that, your bone density and structure would allow for transit back and forth, which would be very hard with Mars. Basically people who lived on Mars and came back to Earth would have a hard time walking around Earth after a couple years. So that's just due to the mass difference. So why is Venus so hot? Again, it's the clouds. It's the greenhouse effect, right? We call it the Hell House world. So we saw here, stated that's about 470 degrees. I'll let you calculate. I think it's about 900 degrees Fahrenheit. But a good question to ask is, why is the greenhouse effect on Venus so much stronger on Earth? Well, you're going to find that there's not a good why. We just observed that we can observe that the carbon dioxide concentration on Venus is much more than Earth, and it's so thick that the surface pressures are 90 times that of Earth. That means that there's 90 atmospheres of pressure on the surface of Venus. And the thick carbon dioxide atmosphere, you'll notice thick being the operative word here, produces an extremely strong greenhouse effect. And again, remember, let's review what greenhouse effect means. A greenhouse gas absorbs heat, and then as heat is re-emitted, so it'll absorb that visible light and re-emit heat, right? And then as that heat is re-emitted, it's absorbed further by the atmosphere and then reabsorbed as more heat. So Earth escapes this fate. Why a question we can ask isn't what happened to Venus to make it look this way, because we don't really know, but why doesn't Earth look this way? And Earth escapes this fate because most of its carbon and water are in rocks and oceans. And that's fundamentally the problem with climate change, is we're taking that carbon dioxide out of the Earth and putting it back in the atmosphere. And that's the issue with burning fossil fuels. Although we've had a very good 3 months, or not 3 months, but 2 months with this one silver lining to this COVID-19 business is that a lot of pollution has kind of cleared itself up. You know, the Earth has managed to rebound very quickly without people, you know, constantly making it dirty. So, you know, that's an interesting side effect that we'll be looking at, that people will be studying for years to come, I'm sure. Yeah, no, I think so too. So reflective clouds contain droplets of sulfuric acid. That's not fun. And the upper atmosphere has fast winds that remain unexplained. So there's a lot we don't know about Venus. But if the winds are fast enough in Venus, that might be helpful in keeping something afloat, like an airplane. I mean, if the wind's blowing fast enough, that'll do it. But you know, it's, you know, someone's got to be pro-colonizing Venus. I suppose that might be me. But yeah. So the runaway greenhouse effect would account for why Venus has so little water. Oh, our sun, yeah, so in about 4 billion years, our sun will explode. We'll talk about the death of our star in a not next week, but probably the week after. And yeah, no, everything dies. That's going to be the overall theme of the course. Planets die, stars die, galaxies die, and eventually universes themselves die. So we just want to look about what that looks like and how that is. So if you wanted something depressing for the day, there you go. But we want to talk about the greenhouse effect more in Venus and sort of bring it back to Earth. Okay. So we've looked at these terrestrial planets and we've seen features and looked at them and sort of seen what they're made out of. One thing I like about looking at this is you'll notice we didn't list too many facts. You can find, for instance, like how long a Venus year is and how long a Mercury year is and how long a Mars year is. You can Google that stuff. What we really got to do is look at what we understand about the planets and the pictures we have of them. And that's sort of the stuff I like. That's one thing I like about planets, is there's more to just talk about because there's so many features to see. But we're going to see that with stars as well. I mean, with stars, we actually understand the inner working of stars pretty well, so it'll seem more technical. But it's actually there's some cool stuff there though that's you know, that we have to look at the consequences of. But one of the questions we have that we're asking about, like Mars in particular, right, is can life exist on these planets? Can these planets support life? And so now that we sort of started this chapter with Earth, and we've talked about our terrestrial planets, and now we're bringing it back to Earth. Okay? And when we look at the Earth as a living planet, we want to look at those features that are unique to Earth that allow life to exist. All right? But then we also want, once we look at those understand those unique features, we also need to understand what our actions are doing to those features and how they're affecting the habitability of our planet. All right? So, the features that are important for life, and Carl Sagan sort of set these down, are climate stability, plate tectonics, atmospheric hydrogen, and surface liquid water. And a lot of these work together too. Okay? So Earth's distance from the sun, we're in this habitable zone, and we have a moderate greenhouse effect, and that makes liquid water possible. All right, so we want to keep the greenhouse effect moderate. The greenhouse effect is too hot, that water evaporates very quickly. Atmospheric oxygen, this allows, or this is one of the things to tell if there is life on a planet, is you can just look for a large oxygen content. that's indicative of life because photosynthesis is required to make high concentrations of oxygen, which produces the protective layer of ozone. So plants will undergo photosynthesis. They'll oxygenate, I think that's right, the atmosphere with O2, and then that O3, over time, that O3 layer will form. Ozone is what this protective layer of O3 is called, can absorb highly charged particles, and it can keep us safe from external, like, cosmic sources of high energy particles. Plate tectonics are an important step in the carbon cycle, the carbon dioxide cycle. So that's one of the things, is if without plate tectonics and moving, without an ability to reabsorb, more greenhouse gas just goes out and out into the atmosphere. And then, of course, we have everyone's favorite, climate stability. All right. Oh, there was no thing in climate stability. Yeah, basically, if you don't have a stable climate, you know, life, there's a lot to be said about life, and a lot of people have a lot of opinions. One thing I can say for sure about life is that it is fragile. We're kind of seeing that now, really, with the whole situation we're in with the virus. But it doesn't take a lot to make things go from comfortable to very, very, very uncomfortable to inhospitable. That slope is not as far as people would like you to think. But that's not meant to scare you. It's just a fact of life, and it's meant to create thought. If we look here, we can see continental motion. We can see the plates, the many plates of Earth that are outlined here. And the motion of continents can actually be measured with global positioning systems. So we actually have a lot more information in the last 15 years or so, since GPS has been launched, about the motion of continents. And continental theory is actually really interesting. The first idea for it actually came from Africa and South America, or an analysis of the maps, because it looks like that South America should fit like a puzzle piece right into Africa. And then so people started looking for more of these ways that things fit together. And that's where motion, models of continental motion came up. And I suggest you, during break or after class, that you look for models of continental motion, because it's pretty cool to see what the Earth looked like before and the models of what it looks like, it's going to look like in the future. You'll notice that the classic Earth, another Doctor Who reference, they call this, in one episode he called this the classic Earth, is not going to be forever. All right. We can see, you can see here that these, like, for instance, these plates are moving past each other. So there's some features of Southern California that will pass up Northern California in a couple 100 million years. And that's pretty interesting. So again, the puzzle-like pieces, it's not a perfect fit, but you know, it was the motivation behind it. So seafloor recycling is a process known as subduction. All right, and I do want to talk a bit about this because we see this in northern North America, like in the Cascade subduction region in particular. Subduction zone events usually are very large earthquakes that usually produce very large tsunamis. So if you remember those large earthquakes that produced tsunamis in the middle of the, not the last decade, but the one before, in the early 2000s, that would, I believe it was 2011 when the Fukushima disaster happened. I'd have to look that up. I can't remember the date. But those were caused by subduction earthquakes in which large amounts of water are displaced. So subduction occurs at ocean trenches where dense seafloor crust here pushes under less dense continental crust, okay, thereby returning to the seafloor crust to the mantle. So you get this recycling where the North American plate is sort of subducting this stuff underneath, and then through this, that comes back and goes into this convection cycle, and then as that subducts, this plate, the Atlantic plate, is stretching, right? so this emits, creating a new ocean floor. All right, and this is seafloor recycling through this process of subduction, and it takes a couple 100 million years for complete recycling of the seafloor. But we can see here a little bit of what I was telling you about. We can see the Earth 200 million years ago, where you'll notice they have this Africa and South America locked up here, and everything was sort of together. You can see that the continent's starting to move apart, and you can see this is our classic Earth. But notice 100 million years from now, things look a little different. You'll notice Antarctica is creeping back up, and you'll notice that Africa eats Europe. So Europe's in for a bad 150 million years. It's not going to make it. So it doesn't look like it actually looks like Europe and the Middle East. This area here, it's probably going to be under Africa. And so enjoy the Mediterranean while you can. Now, the carbon dioxide cycle is one of the main drivers of climate change, climate change on the Earth. Long-term climate change is redundant because climate, unlike weather, is a long-term effect. Weather is the day-to-day changing of what you see outside. It's raining one day, it's not raining the next day. Climate is an overall trend. You look at things like global temperature over a long amount of time, long-term behavior of the Earth. So let's look at sort of the whole cycle. All right, and we have 2 slides that'll go through the whole thing, but we can see here that atmosphere, so if we're in the atmosphere, right, CO2 in the atmosphere can actually be dissolved by rainwater and deposited in the ocean. And so that rainwater goes and is absorbed by these materials, these minerals, they flow into the ocean. The minerals combine with carbon to make rocks on the ocean floor. And as you can see, the subduction carries that carbon down back into the mantle, and then the planet will outgas through volcanoes that gas back into the atmosphere. Now, here's sort of the weird problem. I'm going to draw for a little bit. Here's sort of the weird issue. Think of the amount of carbon dioxide that the Earth can produce, because you might be saying, well, wait a minute, the Earth outgasses lots of CO2. But the Earth's carbon dioxide cycle is like a cup of CO2. All right, so this is the naturally occurring CO2 that's emitted and absorbed. And the Earth can only absorb about as much as it puts out. So if we add, I'm going to put another color, if we change colors here, if we add more carbon dioxide, it might just be a little bit, but if we keep adding little bits more and more, you'll notice that the Earth is also outgassing and emitting the same amount. The concentration of CO2 is increasing in the atmosphere. And the more CO2 we have in the atmosphere, the higher the global temperature gets, and the closer we become to Venus. We don't want to become Venus, right? So the carbon dioxide cycle is important for understanding climate change. And in fact, when I teach climate change, I actually don't look at the temperature changes first. I do teach those, but I really concentrate on carbon dioxide because it's something you count, it's easy to understand and measure, and the effects are non-controversial of the effect of carbon dioxide in any system. In fact, we make greenhouses in the botanical gardens by changing the carbon dioxide content to create different temperatures so that plants that wouldn't normally grow in New York's climate can grow in New York. And we do this all over the world. So the greenhouse effect is an extremely well understood effect. And again, it can all be, as climate change, understanding the basics of climate change are really quite straightforward, and we'll see a couple of them now. I don't get to talk about it the way I really would like to, but everything you have to look at comes back to this concentration of carbon dioxide. And right now we're at about 420 parts per million. That might not sound like much. That means for every million particles of air, only 425 are carbon dioxide. But when carbon dioxide hits but when carbon dioxide reaches 1,000 parts per million, all right, it's going to be really difficult to breathe. Your cases of asthma are going to skyrocket, and if it, I mean, respiratory illnesses will become much more fatal. So if something like this disease had spread, like COVID-19 happened in a Earth where the concentration of CO2 is 1,000 parts per million, it would have been a lot more fatal, almost, assuredly. And at 10,000 parts per million, so that's when the carbon dioxide content is just 1% of the atmosphere. That's still with oxygen being 19% of the atmosphere, nitrogen, or even oxygen still remaining the same, but just losing some nitrogen. At that point, the atmosphere is toxic, and breathing it is deadly. So, yeah. So you don't want to get confused by these numbers or concentrations. Surprisingly small amount of concentrations can be have extremely negative effects. You want to be aware of that, or not just assume. You can't assume 1% is small. Again, there's context is needed there to look at those numbers and think that way. I'd actually wanted to bring up a way to think about the growth of. Actually, I'll bring that up in a little bit. Because we'll have a graph. So long-term climate change. So that being said, the Earth is in a hot period right now, also because of a few orbital resonances that are matching. In about 50,000 years, the Earth is much hotter than it normally is now. So in about 50,000 years, we're gonna absorb all that CO2 back. There's no reason to think we're on a runaway effect, but like to end all life forever. Although there is some, there is a lot of compelling evidence that we're in a sixth mass extinction caused by humans. So the planet might look different, but it with only 3 months, things already look a lot better. Well, at least they look better on the surface, right? There's underlying things that will take decades, if not centuries, to fix. But the question is where are we on a track to make it 50,000 years? Keep in mind that all of recorded history is about 8,000 years, and that the industrial age is only 180 years old. So we have to figure things out. So we can see that the Earth does go through these cycles. Oh wait, I didn't go here. Yeah. Right, and changes to the Earth's axis tilt might lead to ice ages. Of course, these will lower global temperatures by increasing the Earth's reflectivity, and CO2 from outgassing will build up if oceans are frozen, ultimately raising global temperatures. So there's sort of a thermostat here. So now we get to our thing. The CO2 cycle acts like a thermostat for Earth's temperature. That's fine. So again, like I told you when we first looked at them, these features are intertwined, and there are many connections between them. Plate tectonics creates climate stability. Climate stability allows liquid water. Liquid water is necessary for life. Life is necessary for atmospheric oxygen. So all of these features that make life allowable are they're interconnected. So now we get to what I wanted to talk about, how our human activity is changing our planet. I just want to be sure there aren't better graphs coming up here. Let me see. What you're looking at here is a rather interesting graph, and it's a little hard to read. So this is the degrees Celsius above or below 20th century averages. So basically we take an average of 1900 to 2000, right? And we look at whether we're above or below that average. These are changes in temperature, okay? Not absolute temperatures. And you'll notice that, and a lot of times in math or in science in particular, absolute numbers don't help us, or they're not as informative as change. So for instance, if you look at the COVID data on Worldometer, if you look at the absolute cases, it's sort of, we can see that the rate slowed down, right? So if you look at that, you'll, let me get to my pencil. You will notice that the curve of cases looks like this. All right? So it was growing rapidly for a while, but then it sort of took a linear turn. And you've probably heard people say, are we past the peak or in the peak? Now, what we can look at, what's more interesting and informative, is the rate of daily changes, right? There's a graph that will tell you how many people, how many new cases we had. And that graph is starting to look a little like this, right? Where we can look and notice that except for that one day, we're not growing with new cases. So that tells us we're entering the curve, or the height of the curve, all right? Because the change is small. The absolute numbers are still large. We're getting 20,000 cases a day. But we're going to talk a little bit about the growth and the things that are scary with climate change, because it's become very clear to me as an instructor. I thought exponential growth was a little more clear than I think I thought it was, which is too bad, but it's not as clear as I thought it was. Let me just go forward here. I want to see if there's what kind of graphs okay, we're all going to get to those graphs. So we'll talk about that, but one of the worrying parts here, right, is how this curves. Because if it's nonlinear, it can grow incredibly fast in a very short amount of time. But one of the weird things about nonlinear is it gives you the sense, this is why climate change scientists are so concerned, and linear and exponential growth is very understandable with the coronavirus. And so we're going to use that as an example when we look at some other graphs. So human-made, I think these are CFCs, or let's see. Let's look up what a CFC is. I do this every semester. I forget what it is. A chlorofluorocarbon. So these are so that's stuff we release into the atmosphere. Chlorofluorocarbon. All right. In the atmosphere, they destroy ozone, reducing protection from UV radiation. And human activity is driving many other species to extinction. This, unfortunately, we can see. Human use of fossil fuels produces greenhouse gases that increase that carbon dioxide concentration and thus contribute to global warming. Now, the Earth's average temperature has increased in the last 50 years by about ½ degree centigrade. And I like to talk about this because these are the things that I find mildly infuriating, because a lot of people talk about this in a very incorrect manner. You'll notice a lot of people are talking about the virus in a not helpful way for the most part too. So the concentration of CO2 is rising rapidly, right? And an unchecked rise in greenhouse gas will eventually lead to global warming. Here's what I don't like about this statement. It's already led to global warming. Global warming is a past tense, not a future tense thing. We're at ½ degree right now. Okay, the question is by 2100, will we be at 1 degree from the 20th century, 2.5, or 5 degrees? This is the worst case scenario. This is the best case scenario. All of these require humans. We need to adapt. So, unfortunately, what's often said is, and what I heard previously that really gets me going, is people saying, "Oh, they say we only have 10 years to make changes." Well, that's what they said 30 years ago, and we're still here. So, unfortunately, when I was your age, or in the 90s, when they said we have 10 years to make a change, or we're gone beyond point of no return, in 1990, there was a chance to have 0 degrees, to reverse the 5 degree warming and have no effect whatsoever. That time has passed. That is now not a possibility. What we have 10 years to do is avoid 5 degrees. A 5 degree change would almost certainly mean the extinction of the species. 2.5, again, this is at global average temperatures. You can't think of this like in seasons, right? Where the temperatures fluctuate by a lot of degrees and it'll be no big deal. The effects of climate change are already very real, and we feel them. And we've come close a couple times. For instance, the Syrian conflict started because it was too hot for too long and crops failed. And that was the impetus that led to the collapse of that country and why it's still in civil war, essentially. And speaking of depressing things, as we've seen in this country now, even with COVID-19, when food is scarce, people get scared. When people get scared, as we all are experiencing, and some of you may have even experienced, some of these conflicts and things around the world, or scarcity. It's no laughing matter. It's no joke. It's crazy. And basically, an easy way to understand this is that the more these numbers increase, the more scarce resources that make us comfortable will be, and that's just the bottom of the line. So when climate scientists say we have 10 years to avoid the consequences, what they mean is that we have 10 years to avoid 2.5. We're getting to 1. That's unavoidable. There's so much inertia of the climate system that if we all self-distanced and didn't start the economy for 50 years, it would take that long for the CO2 to reabsorb. But when they talk about the 90s and they say, oh, we only had 10 years to act, we did, and we blew it. That was to get to 0 degrees. That was no change. Not an option anymore. That can't happen. So, now what I wanted to talk about here is we can see with this graph, that the change in carbon dioxide is ever so slightly it looks exponential. If it's a straight line, it would be a huge breath of fresh air. But if it's exponential, that's a problem. So think about and the coronavirus makes exponential growth very clear. And the problem with exponential growth is that for a long time, it seems ridiculous. And if you look back to March 11th, okay? In March 11th, there were 1,000 cases of the coronavirus, all right? And people were saying, well, there's only 1,000 cases in a country with 300 million people. It's not a big deal. People are saying, well, it could be. It's a pandemic. It's spreading easily and quickly. And people are like, well, it's only 1,000 cases. By March 22nd, there were 30,000 cases. So it took 11 days to get from 1,000 to 30,000. 30,000 was a lot, but what's scary about exponential growth is then by March 25th, there were 60,000 cases. So it took 11 days to get to the first 30,000. It took 2 days to get to the second 30,000. All right? And now we have 30,000 every day, right? New cases. But that would be worse if the exponential growth got worse, right? Say we didn't flatten the curve and we were on an exponential curve. So that would mean that, if the number of new cases, I originally did a brief analysis, and I sort of came to the conclusion that we almost had to have peaked by last week. That would be the soonest we would peak, because assuming there were 10 times as many cases as are confirmed, basically, if you look at the exponential doubling, right? So say it takes 2 days to double. So if we start at 1,000, we get to 2,000. Well, we'll start with, I'm going to use scientific notation so times 10 to the 3. So say that means it takes 2 days to get to 2,000, another 2 days to get to 4, then another 8, 16. Here we get to 32, right? 32,000. So this takes from 1,000, that's 2, 4, 6, that's 2, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's 12 days. So that's essentially what we saw with COVID, right? Here's the problem. Start doubling in 2 days, we got to 60,000. Another doubling in 2 days, we'll get to 128,000. A lot of people think you just double this. You double the whole amount. So what that means is that sure, you start small and everything looks okay, but if we keep doubling, basically my projection was that if you took the amount of cases in mid-March or late March by about March 20th, you assume that there were 10 times as many cases as there were reported, which is a super conservative number. Then we ran out of people on April 15th. April 15th, if it doubles, that's the date at which 300 million and 380 million people would have the COVID-19. So essentially everyone would have it. And there are some studies that are predicting a much higher rate. So now it's just a lag of testing. And as you can see, if you look at the data, we started flattening out in about 8 days ago. Okay, so exponential growth. If we look at carbon, so let's clear this. If we look at carbon, and if this is exponential, things are going to seem okay for a while, right? It'll be slow, and then we'll get to somewhere like this, and then all of a sudden, it'll be too late to stop it. If it's exponential and if we can't flatten the carbon curve, such to speak, as it were, put it in terms that are a little more modern. If we can't flatten the carbon curve, we're done. And so as much as climate change is about, or COVID, our COVID response, our social distancing is about flattening the infectious curve. We want to flatten the carbon dioxide curve so that the atmosphere can keep reabsorbing enough that we don't endanger life on the planet. I like that. That worked. All right, so it's 4:35. Again, we're doing this a little bit differently. We're just going to take one long break in about 20 minutes. So that helps with the, I don't want there to be too many videos because they can be hard to navigate. So I just want 2 per class. We'll take a short, I'll take a short 3-minute breather, but then we'll take our long break in about, in a little bit. I got to get some more water. So I'll return, but don't go. Get a cup of water or something, and and then I'll be back. But we, at about 5 o'clock, we'll take our long break and stop the water. Ow, that hurt. Okay. All right. So let's keep going, and then at about 5 o'clock, we'll stop recording and we'll take a break till about 5:30, and then we'll do our last hour. Okay. All right. So you'll notice that that these graphs. So one thing to be aware of is that when you're looking at climate graphs, the year 0 is usually 1950. So you have to be careful. You'll notice that's about right here, right? So when it always says today or present, that's where a lot of confusion comes from, because a lot of climate graphs don't take anything into account after 1950 when they're long. Like when you look at these like thousands of years or hundreds of thousands of years ago. Going back to the year 800, present day is generally 1950 or 1960 or something like that. So something to keep track of. Um, uh, so now modeling climate change can be messy business, right? So we have we notice that that when we include in models, in predictive models, when we have carbon dioxide, I believe the black curve is the observation curve. So that's just what we see. And we can predict what it would look like without humans adding everything. So we'd have something like this here. You'll notice the Earth still is in this sort of hotter time. But with when you add human influence, you'll notice the curves match pretty well. So again, when curves match and models match, we tend to look at them. Consequences of climate change. Increases in temperature vary from place to place, and the effects of weather patterns are quite complex. Basically, the Earth becomes less hospitable. Extreme weather events are more common. Droughts are more common. The ability to grow resources comfortably becomes harder to do. So anyhow, I wanted to talk about that, but I didn't want to talk about the habitable zone and planetary density. This stuff is okay, but it's just it's making it a little too technical. I don't think we need to go over all that. All right, so let's. So I noticed I have 17 or 16 people in here now. So I'm loading up the next chapter. I just want to remind everyone the paper has been posted. So please pick a topic tonight by no later than tomorrow. Give me your 4 top choices. All right, so that way, and I will be assigning topics on first come, first serve, and I will post your topic on Wednesday. All right, that's the goal. So it's all on Blackboard, and there's a new activity. No, I don't want Skype. I want. We want new files and share files. Oh, I have to share the. Oh, wait a minute. I have to stop sharing this file. And then I have to go to sharing this file. All right. So we're probably going to fly through this a little bit. We'll talk about features, but a lot of these are pictures. We'll talk about some of the major differences, but I don't want to focus on too much about it. You can really read a lot of it. I don't want to keep stating a bunch of factoids that you can read, but we'll highlight the interesting ones. Okay, so we've talked about the inner solar system planets. We're going to talk about the Jovian planets, all right, and how these giant planets are different than our terrestrial planets. Okay, so here are Jovian planets. You'll notice. Let me get my pointer. You'll notice that here's the Earth, right? The Earth is just a little guy compared to our Jovian planets. And we have 2 sort of big giant ones and 2 medium ones. But even Neptune and Uranus are much, much bigger than the Earth. All right? You'll notice that you have the mass in terms of Earth. Jupiter is by far the biggest planet in the solar system. Its mass is 318 times bigger than that of Earth. And with Saturn about 100 times, and then 14 and 17. So you'll notice these are much smaller. Earth is about 10 times smaller than these planets, and these guns are about 10 times smaller than the big ones. All right, and so we'll look at their compositions and where they get their colors. You'll notice the big planets are mostly hydrogen and helium, and the little ones that are bluish and green have hydrogenic compounds like methane and ammonia. All right, so we saw that, yeah. So basically, the thought process and how these planets get so big is that in addition to the rock and metals that were available to the terrestrial planets, hydrogenic compounds like water and ammonia and methane didn't freeze or didn't vaporize. So they were also solid and can form much bigger cores, and capture a whole lot of the hydrogen and helium gas. So that's why they became so big. Jovian cores are very similar. They're very massive. You'll notice it has 10 Earth masses. So the planet that forms earliest captures the most hydrogen and helium. That means Jupiter is probably the oldest planet. And of course, the location, we notice Jupiter is the biggest one. It's also the closest to the sun of all the Jovian planets, too. Uranus and Neptune are actually denser than Saturn because they have less hydrogen and helium proportionally. And we can see the relative densities of those planets. And the interesting thing about density is compression, right? So Jupiter and Saturn look like they're about the same size, but if you stack pillows, eventually the more pillows you add, the smaller you look, right? Because you'll flatten out those pillows. And so things can be, Saturn, which seems like it's almost of equal size to Jupiter, it's deceptive in its mass because Jupiter is so much more mass that all that gas gets compressed. So let's see, sizes that we don't need to look at that. Like I said, I'll stop on stuff we need to talk about. So one thing I want to look at is the layers of these Jovian planets. Now you'll notice that they don't really have surfaces. They have solid cores, but I want to remind you that a surface or a crust or surface is synonymous with a crust, right? The Earth's got a solid core, but that's not our crust or surface. And then we have a mantle, and we can see here we have the crust in the atmosphere. So Jupiter has these metallic hydrogen, liquid, and gaseous, these three phases of hydrogen layers, but and even though you might be able to argue there's a surface of hydrogen, but even that doesn't really work because there's no plate tectonics. It doesn't create features. There's no mantle for Jupiter. All right, and I want you to notice the pressures are enormous. So at that at the bottom here at Jupiter, or at the bottom, but at the liquid metallic layer, it's 2 million atmospheres. And near the core, it's 100 million atmospheres. And the temperature is about 20,000 degrees Kelvin. All right? So there's a lot of hydrogen packed in here quite a bit. And you'll notice that distance-wise, the Jupiter is just so much bigger. And the only part we can really see are these cloud tops. All right? So why do we think Jupiter looks like this? Well, the core is thought to be made of rock, metals, and hydrogen compounds for a pretty good reason. The main reason is because it's thought that the charged particles, that you could ionize hydrogen in here and create what is a spectacular magnetic field. So Jupiter has an enormous magnetic field. And you'll notice that they have this layer. The Saturn's magnetic field is also pretty big, but they have this metallic layer much smaller because those models look at the magnetic field, all right, which they're not showing. But anyway, we can model and guess, but here we have Jupiter's magnetosphere. So Jupiter's magnetosphere is spectacular, and it protects not only itself from those clouds disappearing, but probably also its moons too. And we're going to talk about moons because the Jupiter and Saturn are almost their own little systems. Well, they really are their own little systems. So Jupiter's very strong magnetic field gives it an enormous magnetosphere. And remember, again, magnetic fields are produced in planets by moving charged particles. And we can see these enormous auroras in Jupiter, which are pretty spectacular. And we can see the Great Red Spot, so we can see weather. So the red spot on Jupiter is like a giant hurricane. But imagine a hurricane the size of Earth, where the winds spin at, I think, actually, I'm going to look that up really quick. Let's see. Wind speeds on Jupiter's Great Spot. There we go. That's one nice thing about doing this way. So they're 384 miles per hour. So that would be like a Category 8 hurricane. Not that such a thing exists, but they're spinning pretty fast. So imagine that a storm 3 times the size of the Earth spinning like that constantly. And the Great Red Spot has been visible for at least 400 years. So that storm isn't dissipating anytime soon. But those are the features of Jupiter that give us insight into what it looks like, right? We can see the magnetic field, so we have an idea of what would be causing such a tremendous magnetic field. And then we see that the storm structure of Jupiter stays relatively static. Sometimes storms last for a couple of years and then go away, but we can also see sort of these constant features and model what we think Jupiter would look like on the inside to lead to the features we see on the outside. Okay? And that's important. So, what's next with Jupiter? So we can see the different colors in Jupiter's atmosphere. They correspond to the freezing points of these different hydrogenic compounds, all right? And other Jovian planets have similar cloud layers, all right? But we see that there's more hydrogen and helium are taken in by the bigger planets than the smaller ones. And again, there is something to be said for just sort of sitting back and sort of really looking at Jupiter. I mean, it's pretty amazing. You can see the red spot there. So we can see that ammonium sulfide will reflect the brown, and ammonia reflects white. So we can see that these are ammonium sulfide clouds, and this is just ammonium. And again, we can look at that stuff too by looking at spectrum. So spectra will give us that type of information. But again, I think this is more interesting to just sort of ooh and ah at Jupiter more than anything else. So Saturn's colors are similar to Jupiter's, right? But they're deeper in and farther from the sun. They're more subdued. And now when we look at methane on Uranus and Neptune, there's much more of that methane clouds than there are hydrogen and helium. So that will lead to the more bluish, greenish flavor of those planets. All right. And you might be wondering why we have such spectacular pictures of Jupiter and Saturn, but not Uranus and Neptune. We've never really been to those two planets except for 1 or 2 missions. I think it might have only been Voyager that went past those in the 70s to take pictures. We've sent many more missions to Saturn and Jupiter. There's more going on there, I guess you could say, than the other ones. And plus, they're closer, so they're easier to get to. All right, because you'll notice again, you'll notice the pictures look, the pictures look very modern, a little less modern. And so these are a little less modern looking, and so this is from the Keck telescope. So this has to deal with some atmospheric stuff, but this is a 40-year-old image from Voyager 2, and we can see storms. And that was like the only time we passed over, but we can see these weather patterns in these Jovian planets. They all have very strong winds. All right, let's get through that. Now, now that we've learned about the planets themselves, why are all those planets labeled or known as Jovian planets? So Jovian planets are thought of as gas giants. That's why they're known as that. I don't know what the Jovian must come from somewhere. I can look that up. What we call they're the gas giants. So Jovian, I believe. So Jovian, I believe, comes from their Jupiter-like. So Jovian seems to be the Roman mythology word for Jupiter, and then so Jupiter's the biggest one, and somewhere someone said, "Oh, these are Jupiter-like planets because they're big and gassy. They're not like the Earth, which are the terrestrial worlds." The better way to classify them is terrestrial planets and gas giant planets, or gaseous planets. That would be a better way to do it. The Jovian part is just because they're Jupiter-like, and we are biased about what we discover here on Earth first. So I think that's actually a good place to take a break, because looking at the planets, that gas giant planets are interesting systems within themselves. And once we start talking about moons, I think we're going to go a lot longer than 10 minutes. So why don't we come back at around a little after 20? So I'm going to stop recording so that the movie can process.